All right, so we just finished working with monomials and how we simplify monomials, specifically how we simplify irrational numbers and simplify complex numbers. So now we're going to move into factoring binomials today, factoring polynomials in general. What we're going to use this for and how this fits kind of into the flow of the course is we're going to use these skills to simplify algebraic expressions, algebraic fractions, right? What did we just finish doing? Irrational fractions and complex fractions. This skill we're going to immediately use to simplify algebraic fractions, but I'm also going to show you along the way how factoring is related to what we talked about at the beginning of the course, the fundamental theorem of algebra, which says that every nth degree polynomial equation has n solutions, n roots. Now, some of you included in your fundamental theorem of algebra papers that it tells us that every polynomial expression is factorable over the complex numbers. The fundamental theorem of algebra does guarantee that. We're going to kind of tie that into this lesson as well. All right? It's a long lesson, some easy stuff beginning, some new stuff in the middle and the end. Okay, so just kind of stick with me. Don't tune out because of the easy stuff at the beginning. We'll want to move, want to keep your attention. So everything is going to tie together. Binomials, two things. Anytime we're told to factor, we're going to use this checklist for factoring. Checklist for factoring for binomials, the first thing we'll look for is GCF. All right, so we'll look at a few just kind of reminders. This is the easy stuff. Okay. The next thing we're going to look for is a difference of squares, right? So all you guys remember difference of squares. The first problem that we're going to look at, everybody's going to know how to do it. Everybody's going to know how to do beyond that. We're going to add some applications of that concept, difference of squares. And then a new concept for you is going to be factoring of cubes. Okay, that's what we're doing today. Trinomials, we'll do GCF and trial and error factoring. While I'm on the subject, we will not use circle, slide, divide. I will not have any mercy on you when you choose to use that technique and miss the problem. All right?
Yeah. I can't.
So I need to make sure that you guys are kind of aware of that at the beginning. We're going to use a good old trial and error, unfoiling method to factor, but that's the next lesson. Okay, so binomials, we'll factor a GCF, then we'll look for difference of squares, and then we'll look for cubes in that order. I'm not going to use the checklist out of orders. Always look for a GCF, always look for difference of squares, always look for cubes in that order. Okay, so what does a GCF look like?
Greatest common factor.
All right, it's the greatest common factor, so you can just kind of ignore all this stuff. What does x squared plus 7x, what do the two terms in that expression have in common as a factor? X, right? They have an x, and so we can factor out the x, and when we factor out the x, what's left behind? X plus 7. So x squared plus 7x will factor as x times x plus 7. Okay, so some binomial expressions only have a GCF that we can take out. We can't factor x and x plus 7 any further. We don't need to, because what do we see in x and x plus 7? What do we have here? That's the two factors that will give us the two roots of f of x equals x squared plus 7x. X equals 0 and x equals negative 7, right? We don't need to factor it any further because we've gotten to the place where we can find the two zeros of that polynomial expression. All right, what about this one? Now, this one is a trinomial. Right? But we can still factor a GCF out. That's the first thing we would look for if we were working with a trinomial expression. 2x is the greatest common factor. Does everybody agree with that? So if we take out a 2x, what's left behind?
2x
plus minus 4, right? So 2x squared plus x minus 4. Now, what can we always do to make sure that we factored an expression correctly and completely.
Multiply it back out.
Right, you can multiply it back out to see if you factored it correctly. To see if you factored it completely, you just kind of have to go through the factoring checklist. So really, once we start factoring trinomials, we'll need to make sure that this trinomial that results right here, 2x squared plus x minus 4, isn't factorable further. Okay? And I'm going to give you a technique to determine really quickly if it's factorable or not. All right, so GCF is the first thing we look for if we're factoring binomials. The next thing we look for is difference of squares. Okay, can somebody give me an example of a difference of squares? Drew?
X plus 2 times x minus 2.
Okay, that's the factorization of it. What would it be if you multiplied x plus 2 times x minus 2 together?
X squared minus is 2.
X squared minus 4. 2 times 2 is 4, right? So x squared minus 4 is an example of a difference of squares. X squared minus 25 is an example of a difference of squares. And everybody in here, this is what I'm telling you, this first part's really easy. Everybody in here knows that x squared minus 25 factors as what?
X plus 5, x minus
X plus 5 times x minus 5 is correct. Okay? So, how do we identify whether something is a difference of squares or not?
Well, if it has a negative, it has to be a negative, and it has to be a perfect square.
All right, so let's look at this. So you're right, Drew. If we have to say, is the first term a perfect square? All right, we have to determine if the exponents are all squares. How do you determine if an exponent is a perfect square or not? Exponents that are perfect squares are what kind of numbers?
Rational.
Perfect squares have to have what kind of exponents?
Positive.
No. They have to be
Whole.
even. Yeah, even numbers are perfect squares. Right? Because remember, the square root of something is the same thing as raising it to the 1/2 power. Okay? So in order for this, if this was x to the a, then that's x to the a over 2. So in order for that to be a perfect square, we would need a to be divisible by 2, which means it has to be even. Okay? So even exponents tells us that we have squares. All right? So we need the first term to be a perfect square. We need the second term to be a perfect square. And we need the two terms to have different signs. Now, Drew, you just mentioned that we needed to have a negative in between them.
Yeah,
It doesn't necessarily have to be in between them, right? We could have this expression could be written as negative 25 plus x squared, but we could also have something like this, negative x squared plus 25. Negative x squared plus 25 is the same thing as 25 minus x squared. So they just have to have different signs in order to technically be a difference.
Here, we're not number, what would that be called?
Term.
Each term has to have an opposite value of the other.
Has to have an opposite sign, that's
It
correct.
doesn't matter which one it is.
Right.
Because and the only reason it doesn't seem like that in the original problem is because the negative's in between them, but the first term is positive.
First term's positive, second term's negative. Good. Yes, that's correct. Now, so 25 minus x squared would factor as 5 plus x times 5 minus x, correct?
C.
All right, so we've got a difference of squares there, even though it's written differently. All right, so difference of squares, the first term has to be a perfect square, the second term has to be a perfect square, and the two terms have to have different signs in order to be a difference of squares, okay? All right, so if the answer of all these three questions is yes, then we have a difference of squares. And difference of squares, very important here, we've been talking about this since day one. Difference of squares will factor into the conjugates of the square roots. Okay? Conjugates of the square roots. The difference of squares will always factor into conjugate pairs, and those pairs of numbers will be the square roots of the two terms. So this is the rules that you guys already know, factoring the difference of squares, but I want to make sure you just really know the rules because of the application that we're going to take it to. Okay, so x squared minus 25 factors as, like we already said, x plus 5 times x minus 5. Why?
does it factor like that?
Yeah. I don't want you to tell me that because the rules say so. Why does this factor? Why does it factor?
Because you have a 5x and maybe 5x, and those two cancel out, so you just have to
Those cancel out, but it multiplies back together to get what we started with, so that is the correct factorization. But the reason that this factors as two first-degree terms is because the fundamental theorem of algebra guarantees that from the two roots of this second-degree polynomial expression, we can get two factors. All right? I want you to kind of keep that in mind, that this ties into what we're doing with the overview of the course. So, a little practice, difference of squares. X squared minus 49 would factor as what?
X minus 7 times X plus
X
7.
minus 7 times X plus 7, or X plus 7 times X minus 7. The order of the conjugate pairs does not matter. Okay? What about 4x squared minus 9y squared? How is this one different?
That's a Y.
It has a y, so all of a sudden this little thing, we can use this to practice our factoring skills, but we lose the practical application of the fundamental theorem of algebra. This is a two variable expression, so if it had roots or solutions in an equation, they would be points. They'd have to have an x and a y, right? So this kind of takes us out of the fundamental theorem of algebra thing, but we could still practice the skill of factoring. Is this a difference of squares?
No.
Yes. 4x squared is a square and 9y squared is the square. So this will factor as the product of the conjugates of the square roots.
So it'd be 4x times
2x plus 3y,
square
2x minus 3y. Conjugates. 2x plus 3y times 2x minus 3y is what we get when we factor this expression. Okay? All right, what about this one? 25x to the 6th minus 1.
No. Oh,
Why do you not think so, Drew?
well, I know it has an even exponent and 2 is different. Like
Is 25 a square? Is 1 a square? Yes, it is. So this is the difference of squares, right?
The whole solve.
What's the square? We're not trying to solve it. We're trying to factor it. What is the factorization of 25x to the 6th minus 1 using the
5x cubed plus 1, 5x cubed minus
5x cubed plus 1 times 5x cubed minus 1? Now,
Oh, that's right.
all right, Drew, I want to kind of take a step back here and address what you just said, because we could talk about solving an equation related to 25x to the 6th minus 1. We could say that 25x to the 6th minus 1, if we want to find the zeros, how many does it have? 6. Why does it have 6 solutions? The fundamental theorem of algebra says that a 6th-degree polynomial equation has 6 roots. Because it has 6 roots, we could factor it completely into 6 linear factors. We're not going to do that with one like this, but we could solve this, couldn't we? We could take this and say it's 5x cubed minus 1 times 5x cubed plus 1. And then each of these factors has 3 solutions, right? There's 3 solutions there and 3 solutions here. We could find those solutions by setting this equal to 0. 5x cubed minus 1 equals 0 means 5x cubed equals 1, which means x is the cube root of 1/5. How many cube roots does 1/5 have? 3 cube roots. So there's 3 of these answers. We'll figure out how to find all 3 of those at some point. Okay? And then 5x cubed plus 1, set that equal to 0. You get 5x cubed equals negative 1. X cubed equals x equals the cube root of negative 1/5, which is okay, right? We can take the cube root of a negative number. So if we're talking about zeros, if we're talking about solving something, this skill is very applicable to the process. Okay? Now, nobody knows what the cube root of 1/5 is. It's an irrational number, but you go. All right, so there's the connection. Keep the connection. What is algebra? It's the branch of mathematics where we learn all the skills necessary to solve all types of polynomial expressions. And if we can find the roots, we can find the factors. So it's very, very closely related to the fundamental theorem of algebra. All right, so x squared plus 36. Can we factor this as a difference of squares? Oopsie. Because they have the same sign, right? The three conditions mean the two things have to be squares and they have to have different signs. Do these have different signs? No. Now, that being said, Drew, what's the degree of this polynomial expression? It's the second degree, and the fundamental theorem of algebra guarantees us that it has two answers, right? And I just told you that we can use those two answers to factor it. So now that we have this increased algebra knowledge over what we knew in Algebra 2 and Algebra 1, I want you to be able to take this expression and I want you to say that it's not factorable over the real numbers. All right? This has two complex solutions, and we could factor it using those two complex solutions, and I'm going to show you how in just a few minutes. But what I would want you to write here is that this is not factorable over the real numbers. Or I'm going to give you the tools to actually factor it using complex numbers. It's pretty easy. Okay? Is everybody clear on that? So the fundamental theorem doesn't break down. The fundamental theorem of algebra allows us to use complex numbers to factor expressions and find solutions. All right, so what about these new concept here? This is a new concept. This is an important concept. For calculus, those of you who are about to take trig next semester and then you're going into calculus 1, you're going to need this skill that I'm about to show you. So I want you to really pay attention to it. Really pay attention to it. This new concept tells us that every difference is a difference of squares if we're allowed to factor over the irrational numbers. Like what we've done so far, we're just looking for the squares of rational numbers. 6 squared is 36. 25. 5 squared is 25. So x squared minus 36 is x plus 6, x minus 6. Those are perfect squares. But doesn't 5 have a square root?
Yes.
Yeah, right? So 5 is the square of something, and this can still factor as the product of the conjugate of the squares of these two things. So watch this. What's the square root of x squared? X. What's the square root of 5? Square root of 5. So we can factor this as x plus the square root of 5, x minus the square root of 5. Very, very, very useful skill in calculus. And I'm going to show you why in just a second. I'm going to show you something that how this is applicable to us. Anybody in here had pre-cal yet? No pre-cal? Okay. All right. So nobody will have seen what I'm about to show you, but it's true. So using this same thing, what would x squared minus 7 factor as? Plus the square root of 7, x minus the square root of 7. Okay? Is everybody good? You catch that? All right?
I don't understand why you have to put the root in there.
Well, because we are following the rule, right? What's the rule for factoring difference of squares?
Every difference is a difference over squares.
The rule for factoring difference of squares is that a difference of squares, Drew, is the product of the conjugates of the square roots. So what's the square root of 5? It's the square root of 5. The square root of x squared is x. Okay, now where we're going with this, y'all watch. Where we're going with this is we can take an expression like x minus 2, which is simplified, right? It's a first degree. What's its root?
1.
The root is
X.
2.
Oh, I thought
That's what makes it 0, right? What makes it 0? If we're talking about the root of this polynomial expression and we're talking about, it's what makes it 0. The 0 of x minus 2 is x equals 2. Okay? But this will factor as a difference of squares. The difference of squares will factor as the square root of x plus the square root of 2 times the square root of x minus the square root of 2, just using the rules that every difference is a difference of squares, and that we factor difference of squares by multiplying the conjugates of the square roots. All right? Now, y'all don't lose me. There's a concept in calculus that is called limits. I'm going to show you just a quick example of how you do limits. The limit as x approaches 2 of x squared over x plus 1 is equal to, you just plug the 2 in, it's called direct substitution. You plug the 2 in and you get 2 squared over 3, right, which is 4/3. All right, this is direct substitution of limits. Okay? That's easy, right? Here's where it gets a little bit complicated. Where limits get complicated is if we were talking about taking the limit as x approaches 2, is how you read that, of x minus 2 over the square root of x minus the square root of 2. Now, what happens if we try to do a direct substitution of x equals 2 into this expression? What do we get in the numerator? 2 minus 2 is 0. What do we get in the denominator? The square root of 2 minus the square root of 2 is 0.
Because it would be 2 over 2.
Right. So that's bad, right? 0 over 0 is not a defined value. Now, what you have to do in calculus is you have to recognize that numerator, because it is a difference, that numerator will factor as a difference of squares. Factor as the product of the conjugates of the square roots. All right, does everybody see what I just did? I factored the numerator as a difference of squares. Every difference is a difference of squares. So what can we do now? We can cancel these like factors. And I can plug in the 2, and what do we get? Square root of 2 plus the square root of 2 is 2 square roots of 2. So I can evaluate the limit by factoring that difference as a difference of squares. For all of you who have taken calculus, you really, really need to kind of see this concept and know it. Okay? So being able to factor things as a difference of squares is an important skill. Another new concept. Every binomial is a difference of squares if we're allowed to factor them over the complex numbers. This is important. You got to write this down. Y'all tune back in. That last little part about limits and factoring every difference as a difference of squares is not testable in this class, but it is an important concept for you later. Okay, x squared plus 25 is a polynomial expression that has 2 roots, right? The fact of the matter is the 2 roots are complex. Now here's how I want you to kind of see this. X squared plus 25 is
X plus 5 times 8 plus 5.
no, that would be x squared plus 10x plus 25. Because you'd have a middle term, x plus 5 times x plus 5. X squared plus 25 is the same as, y'all watch, x squared minus 25 I squared. Right? Because what's negative 25 I squared has a value of positive 25, right? So we could factor this as x plus 5i times x minus 5i. Okay? And then likewise, if we went all the way back to that x squared plus 36 that we had earlier, x squared plus 36 is x squared minus 36i squared. So it would factor as x plus 6i times x minus 6i. So I want you to either factor an expression like x squared plus 25, or I want you to tell me that it's not factorable over the real numbers. but we're not going to say any longer that it's just not factorable, because it is factorable.
That used to bother me so much. Like, I always felt like there was another way to factor it out.
Well, there has to be, right? The fundamental theorem of algebra guarantees me there's two roots, and here's the two roots, negative 5i and positive 5i. So we can use the roots to factor the expression. Okay? All right, now what about the next one? X squared plus 17, x squared plus 17. Now this one kind of is a combination of the irrational and the, right? We can take this and we could see it as x squared minus 17i squared, right? And that will factor as a conjugate product of the conjugate of the square roots. Okay, so the square root of x squared is x and x. Square root of 17, square root of 17. And the square root of I squared is I. So x plus I times the square root of 17, x minus I times the square root of 17. So every binomial, whether it's a sum or a difference, is factorable over the complex numbers. Okay, yes?
What would happen if you put the I under the square root?
All right, the I can't go under the square root.
Just can't?
It just like this, because if you, and that's why I put it in front, because I want it to be clearly delineated that I is not underneath that radical. Okay? Now, if it's clear to me that it's not, that would be okay, but it's just a lot safer to throw that thing in the front and write it like that. Pain?
Perfect square like 25, just put it under the square root.
Yeah, we're going to take the square root of it. That's what we did before, right? What's the square root of 25 is 5. The square root of 17 is the square root of 17. Okay? All right, so that's a new concept. Here's the last thing for the day. This is new also. This is new for everybody. I've discovered that you guys did not do cubes in Algebra 2. That's okay. Wow. If you had me for Honors Algebra 1, you would have done it. Did anybody have me for Honors Algebra 1?
Come on, Slate.
Did you have Honors Algebra 1, Zach? You didn't, did you? Okay. All right. Are y'all ready? X cubed plus 8 is cubes. It's not squares, right? Do we have a GCF?
No.
Do we have different squares? No. Don't have squares. 8's not a square. X cubed is not a square. So we need to talk about how to identify cubes, but we've got to also be very sure to check for GCF and difference of squares before we look for cubes. If you factor cubes before you factor squares, you create a mess. Here's an example of that, and this is a test question. Y'all listen to me? This actual question will be on the next test. Factor x cubed minus 64. That's on the next, not x cubed, sorry, x to the 6th minus 64.
Yes.
X to the 6th minus 64 is cubes, right? X squared and 4, right? But it's also squares, because 64 is a square and 6 is even. Okay, if we factored that, we would factor it as a difference of squares first. X cubed plus 8 times x cubed minus 8. All right, and then you'll see right here we have x cubed plus 8, which is the same as that one, the problem that we're working on factoring right now. Okay, so it's very important to do the square roots first, the difference of squares, before you do cubes. All right, so let's look at this. Here's the deciding what the cubes are. What are the cubes? How do we identify cubes? 2 cubed is 8. 3 cubed is 27. 4 cubed is 64. 5 cubed is 125. 6 cubed is 216. We got to know through 6. It wouldn't hurt to know 7 cubed is 343. If you're familiar with the cubes, then it's really quick to recognize the cubes. How do we tell if an exponent is a cube? It has to be divisible by 3. Square roots are divisible by 2. Exponents or cubes are divisible by 3.
Would 66 be divisible by 3?
No. Okay, so x cubed plus 8 are these cubes? Is x cubed plus 8? Are we talking about two cubes here? Yes. All right, so here's the process. If we have cubes, the first step, cubes will always factor as a product of a binomial times a trinomial. So we're going to create our framework. So vitally important. Knowing where to start this process is just extremely important. Cubes will always factor as a binomial times a trinomial. So what do we have here? We have 5 blanks to fill in, right? We've got 5 blanks here. 1, 2, 3, 4, 5, and 3 signs. So we just got to know how to fill the blanks in. And I bet everybody in here can tell me what those first 2 blanks have to be. X and 2. Right? It's the cube roots. So the first 2 blanks are always the cube roots of the 2 things. So the cube roots of x cubed and 8 are x and 2. Now I bet with just a little bit of thought that you guys could figure out what goes in the first term, the first and the third, right? What has to go in that first term? X squared, because we have to multiply x by something to get x cubed. It's got to be x squared. What has to go in the last blank? Because 2 times something has to be 8. So it's just a matter of what goes in the middle blank. So the first 2 blanks are the square root, the cube roots rather. The next 3 blanks, we're going to square the first, square the last, and multiply. So these next 3 blanks, we're going to square, multiply, square. What do we get when we square x? X squared. What do we get when we multiply x by 2? 2x. What do we get when we square 2? 4. So that's what goes in those 3 blanks.
We've done this before.
We did it day 2 or 3 of class on the sideboard. I showed you guys how to do this. So square, multiply, square. Now what's missing? The signs. Okay, for the signs, we're going to do SOP. SOP, bruh. All right, so SOP means same, opposite, positive. So the 3 signs, the first one is the same as the original sign. So in this case, that's going to be plus. The second one is the opposite of the original sign, which is going to be minus. And the third one is always positive. So same, opposite, positive. Right? Signs are always same, opposite, positive. So let's talk about the process again. Once you identify that you have cubes, it's a binomial times a trinomial. The binomial is the cube roots. The trinomial, square, multiply, square. Signs are same, opposite, positive. Okay, let's put this algorithm to use in a couple of examples and we'll be done for the day. X cubed minus 64. Yes?
Wait. Never mind. I figured it out.
Okay. I think I know what you're about to ask, and let's talk about this because I forgot to go back into this. Here's one of the answers, right? We can see that answer. What's that answer? -2, right? So what we're looking for here are if we're talking about the 3 roots of this thing, one of them is -2. It's the cube root of -8. To find the other 2 cube roots of -8, we'd have to solve this quadratic equation using the quadratic formula. Now, this is an important concept. If we have cubes and we factor things correctly, this trinomial here will never be factorable over the real numbers. So we don't have to worry about trying to factor it further.
So you're just going to leave it like that?
That's right. It is never factorable. When we graph cubic functions, you'll be able to see this. There's only one real intercept, x-intercept. All right, so x cubed minus 64. Are these cubes? Yes, right? So cubes will always factor as a binomial times a trinomial. I got to fill in these two blanks. What goes in the first two blanks? The cube roots, x and 4. The next three blanks are, everybody say it, square, multiply, square. Square the first term, we get x squared. Multiply them together, we get 4x. Square 4, we get 16. Signs are same, opposite, positive. So that'll be negative, positive, positive. SOP. Right? Now, we could convince ourselves of this by multiplying it out, but let's not for sake of time. If you multiply that out real quickly, you'd get x cubed minus 64. I promise. All right? What about this one? X cubed plus 125. Everybody try x cubed plus 125. No GCF, no difference of squares. Okay, is it cubes? Yes. Yes. How many of you have the answer? Let me see your hands. Okay. Amara, tell me what the answer is.
X plus 5.
Yeah?
Plus, parentheses, x squared minus 5x plus 25.
That's right. X plus 5 times x squared minus 5x plus 25. X and 5 are the cube roots. Square, multiply, square. X squared, 5x, 25. Signs are same, opposite, positive. Positive, negative, positive in this case. Okay? Last one. Now, this one, again, we've left polynomial world. We've got a function in two variables. We're not really using roots. Fundamental theorem of algebra is out of the picture here. But we can still use this skill to factor this if it's cubes. All right? Leave yourself some room because this one takes up a little space. Do we have cubes here? We know that because the coefficients are cubes and the exponents are divisible by 3. Okay? So because we have cubes, this will factor as a binomial times a trinomial. What goes in the first two blanks? The cube roots, right? 5x squared and 3y to the 5th. Cube roots is dividing the exponent by 3.
And you're going to go same sign.
No, let's don't do signs. Let's fill in the next three blanks. Let's keep our order the same. All right? Take the cube roots, then square, multiply, square. Square 5x squared, you get 25x to the what? 4th. If you multiply these two things together, you get...
You're not going to do the y.
You get, if you multiply these two things together, what do you get? 15x squared y to the 5th. Square, multiply, square. Then if you square y to the 5th, 3y to the 5th, you get 9y to the 10th. Signs are same, the opposite of that, and positive. Okay? It's not difficult. It's just you have to memorize the process. Okay?
And the thing that messed me up is I was thinking you do something with y on the
No.
second step.
Yeah.
So it's gonna
All right, so there's your homework for this. Now, I want to remind you guys, this homework's going to push you. Some of them are going to be easy problems. Some of them are going to be problems where you have to look at it, examine it, take the concepts you learned in class today, and apply them. My homework's always a little more complicated than the lesson itself. Page 71, 1 through 4, 40 through 48, even. 58 through 64, even. And then 65, 69, 77, and 71.
Do you have a problem with us